Okay, so just a brief outline of what I'm going to talk about. First of all, the motivations behind designing this type of new test. So most of you may be familiar already with nano-indentation as a technique. So Nano-impact has actually been designed as a complementary technique to give you more information about the samples that you're testing. I have a short discussion of the benefits of this kind of nanoscale testing versus the more conventional macro-scale tests. A short explanation of the principles of operation, so how this technique works for us, and then a few examples of how this has been applied to different problems from various users of ours. So for those of you who attended Jeffrey's talk yesterday, he gave a very good overview of nano-indentation as a technique, so I'm not going to dwell on this too much. But essentially, for those of you who missed that, in nano-indentation you take a probe of well-known geometry, you place it on the surface of the sample and you apply a load. How this differs from older, more conventional techniques is that while you're applying that load, you also measure the displacement. So then you can analyse that data to get hardness and elastic modulus information for those samples. The motivation behind developing nano-impact as a technique is that this only gives you information from a very low range of strain rates, so only up around 10 to the 1 at the very high loading rates. What we can do is expand the strain rates all the way up to 10 to the 6. So this is designed to allow you to evaluate the properties of your samples for their real-life applications. Obviously, in any application where the material is going to be part of a moving system, you might experience very high strain rate contacts. So what this testing allows you to do is to evaluate the behaviour under that same regime. We can extend the indentation testing to look at the high temperature indentation values for those samples. So again, not all materials in their real world applications work at room temperature, so it's important to know how those materials are going to behave as you increase the temperature. And then by combining these two techniques, we can do high temperature impact. So this has been designed specifically to look at the real world application for these kind of materials. So as I mentioned, I'm just going to start with a brief discussion of the conventional impact techniques and how this nano-impact technique compares to those. So on the macro scale, you have this kind of Sharpie test. So you have a large metal hammer, essentially. You raise that up, use a mass, and it swings into your sample surface, causing an impact crater. Okay, so this is a very destructive test. You don't get any kind of fatigue information. You just see how much damage there is from that single impact. Using nano-impact, we can make very localized tests. We can also use lower forces to get repetitive damage at a single point. And because we can get depth information at the same time, we can actually look at the fatigue behavior of the sample under this kind of test regime. So these tests shown on the slide are around 50 microns apart on a coated sample. So a lot of words on this slide, an overview really of the benefits and the different aspects of the different testing techniques at different loads. But the key thing I want to point out here is this thing. So essentially with these kind of impact tests, these nano-impact tests, combining the depth sensing indentation with these high strain rates, you can get fatigue and wear behaviour for very thin coatings and films. So now a quick talk about the principles of operation. What makes these tests possible on our instrument is the unique design of the loading head. So the loading head on our instrument is based around this pendulum design. So the force is applied with electromagnetic force actuation. Any voltage applied to this coil moves it into the permanent magnet, which revolves the pendulum around the pivot and applies a load here at the loading head. So we have two ways of doing these impact experiments. The first way is to have a probe-based impact where we actually move this probe back and let it accelerate into the surface. The second way is to have a sample oscillation impact. So to oscillate this sample at a known frequency and amplitude and measure the damage of the surface that way. For the probe-based impact, what we use is an electromagnet at the bottom of the pendulum to pull this back. We then turn that electromagnet off, allowing the indenter to accelerate back into the surface of the sample at a known accelerating force. As I mentioned, with the sample oscillation impact, what we do is we apply a known frequency and amplitude of oscillation to the sample and measure the change in depth over time. What I'm going to focus on today is the probe-based impact, because this is the kind of testing that allows you to get the very high strain rates for these tests. So there are actually two ways that you can perform this kind of probe-based impact test. The first way we have of doing this is simply using a single impact. So you pull the probe away from the surface, release it once, and measure the change in depth and how that damps over time. So this can tell you a lot about the energy damping properties of different materials. So the example on the screen here is from some work done at MIT on ballistics gels for phantoms in ballistics tests. So these are used to simulate organic tissue in order to allow the development of better body armour. So it's important that the synthetic materials used replicate very closely the damping behaviour of these, energy damping behaviour of these biological tissues. So what you're looking at on the trace here is the penetration depth on the vertical axis against time. So you can see this data captures over a very short period. So we have a very high data capture rate in order to allow us to get this information. So you can see on the initial impact there's quite a large penetration to the surface, and then slowly over time you get a damped harmonic oscillation as the probe settles on the surface. Or more accurately, settles into the impact crater. So you can analyse this data or look at this data in two ways. First, as a qualitative assessment. So just by looking at these traces, you can say that the heart tissue, for example, has a very similar damping behaviour to the 50-50 tri-diblock sample. And similarly, the liver is similar to one of the others. I forget which one, I apologise. So what's important here is that not the initial penetration is exactly the same, but actually the damping behaviour, so the recovery of the sample after the impact. So you can also analyse this data. So by looking at the rate of change of displacement after initial contact, you can actually evaluate what the impact velocity was for this impact. And by doing that, knowing the probe radius, the probe area, you can look at the impact energies. Now, the critical thing in this test is that obviously the impact velocities are well outside the ballistic range. So you would say from that it's not a particularly good test for establishing how good these samples would be for that kind of ballistics test. But because the contact areas are relatively low, the strain rate energy densities are within the ballistic range. So for these tests, quite a large radius probe was used. That's because the gels themselves are very soft and we wanted to try and keep the penetration depth as low as possible. You can modify the strain rate during your test by actually changing the sharpness of the sample and the sharpness of the indenter and the depth of the penetration. So you can see with quite a large radius sphere, we can only achieve relatively low strain rates, but by moving to a much sharper cube corner type indenter, we can get strain rates right up to 10 to the 6. So that's using a single impact to look at the damping behaviour, the energy damping behaviour of different samples. The second way that we run this kind of experiment is to perform many impacts at a single point. So again, what you're looking at here is penetration depth against time. This particular experiment runs over around 5 minutes. So during that time, the indenter will be pulled away from the surface, held away for about 1 second, and then released to settle on the surface for a second. So this plot here shows around 150 separate impacts. So for the first impact, you get this initial surface damage. So on that first impact, the indenter moves around a micron into the surface. In consecutive impacts, you actually get a stable period, so a fatigue period, where the indenter is actually impacting on the coating surface. So in this case, it's a titanium nitride coating. After around 60 seconds for this sample, you get a fracture of the coating. So the coating fails completely. So then the indenter moves through to the substrate. So this final portion of the test is actually the indenter just moving slowly into the substrate material. So this is a very interesting test, but on its own it doesn't really give us much useful information unless you can use it in some way to relate to other more conventional type tests in order to allow you to establish performance for different real-world applications. So the results shown on screen at the moment are results from an end milling test on steels. So these are used to evaluate newly developed tool coatings in terms of how they will perform in certain types of tooling wear. So the plot here is flank wear against length of cut, and you can see we have two coatings. So we have a titanium aluminium nitride coating and an aluminium chromium nitride coating. And what this plot is showing is that you get much faster wear of the titanium aluminium nitride coating than the aluminium chromium nitride. Now on the plot we have the results from exactly the same two samples, but this time using Nano-impact. So this Nano-impact test again runs over 5 minutes. The end milling test will actually run over many days or possibly even weeks in order to get the same kind of data. So what I want to bring you attention to here is this first portion of the test, the impact test. So you can see that the ranking of the two samples in terms of rate of wear is exactly the same as the end milling test. And also the shape of the wear, if you like, the speed of the wear is exactly the same. So what this potentially allows us to do is rapidly evaluate new coatings in order to determine how they might perform in longer term tests in order to reduce the amount of experimental time needed. Okay, as I mentioned at the start, room temperature properties do not tell you everything you need to know about a sample. So we have developed a way of performing these kinds of tests at high temperatures. For our high temperature experiments, we use both a heated sample and a heated indenter. The reason why we do this is so that we can match perfectly the sample and indenter temperatures so that you don't get any heat transfer on contact. Any heat transfer on contact between the indenter and sample will lead to an expansion of the tip, which will be measured as a change in depth, so you get massive drift in systems where you don't have tip heating. So we can use this for a variety of applications. So this is this is a fuel cell seal material, which has been annealed at different temperature or at the same temperature for different durations. Okay, so what this does is initially at room temperature it dramatically modifies the hardness of the seal material that's been treated for longer. So it actually has a lower room temperature hardness. But the actual operating temperature of these fuel cells is significantly higher. So it's important to know how this changes. So what you see here is that although initially at room temperature the hardness of the longer treated material is lower, as the test temperature increases, the stability is better. You can also use these high temperature tests to look at the long-term creep behavior of different samples. So that's what's shown on the right-hand plot. So these are raw dwell data from creep tests done to a maximum load, a hold of that load for around 120 seconds. So you have some initial loading rate dependent penetration and then actual creep behavior of these samples. So you can see for the sample that was treated for less time, you get much more creep, so around 800 nanometers of creep compared to 400 nanometers on the longer treated sample. Going back to this particular application with tool coatings, where this can be important is these coatings are developed to be very hard at room temperature. So from room temperature testing, we would say that actually the titanium aluminium nitride sample would be potentially better than the aluminium chromium nitride. During their actual use, you get frictional heating of the tool piece. So the actual working temperature might be much higher than your room temperature evaluation. So you can see here, again, even though the titanium aluminium nitride is better at room temperature, or harder at least, the property or the hardness drops off very quickly, whereas the aluminium chromium nitride sample is much more stable. So we could combine this with impact testing in order to get fracture probabilities at different temperatures. So when I say fracture probability, what I mean is the percentage chance of getting a failure during a 5-minute impact test in this case. So you can see on Different types of coating. So these are titanium aluminium nitride and aluminium titanium nitride. So two slightly different recipes of coating. But you can see clearly you get a much different response to this kind of impact test at the same load depending on the temperature you test at. So at room temperature, the titanium aluminium nitride coating fails very quickly and dramatically, settling down to around 2 micron final depth. At 500 degrees, the softening of the coating has actually helped the load support in this case, so you get a much longer fatigue period and a much less dramatic failure. So the force applied to the surface can be distributed more evenly at higher temperatures. So again, we can use this to compare different coatings. So we have a fracture probability for the two coatings at 25 and 500. And in both cases, you can see that actually at the increased temperature, the resistance to this kind of damage is much better. As well as using it as a technique in its own right, you can actually combine this with conventional indentation as a complementary technique. So here we have 5 slightly different coating recipes, all titanium coatings again. And we're looking at the differences that those different coating compositions have on both the mechanical properties but also the impact response at different loads. So what they've found is that at low temperatures there's a nice correlation between the high H/E coatings and resistance to that impact damage. What is interesting, so this is just a larger slide of one of those. So this is the 5 millinewton impact accelerating force. So you see there's a clear difference between coatings which behave very well in this, so you get that initial surface damage, then a fatigue period with no failure, to some of the other coatings which showed very dramatic failures during these 5 millinewton tests. What's interesting is that if you increase the impact load, those trends don't necessarily stay the same. So some coatings will show a very good resistance to low strain rate impacts. But as you increase that strain rate in the impact, they actually get much more dramatic failures than some of the other coatings which performed less well at the lower impact forces. So just to summarise, you can use nano-impact as a complementary technique to conventional indentation testing, or you can use it as a standalone technique in order to get information that you just can't get using that kind of standard indentation test. You can get significantly higher strain rates for both single impacts and multiple impacts, allowing you to look at the energy damping behaviour but also the fatigue behaviour of different systems. These results have been correlated well with field trials from other techniques, and they can be done in a range of different environmental conditions in order to allow you to look at true in-service performance for these different systems. Thank you very much for your time.
We have some time for a few questions. So the fracture, I was trying to understand this. You're actually mentioning, presenting the probability of having a fracture event.
Yes.
That's what you're looking at.
Yeah, so we found, obviously, depending on, there'll be slight variations in the structure across the surface, so you're never going to get a uniform failure. Right. So it's easier to look at, you know, the percentage, the chance of actually driving a failure. So it tends to work quite well as a categorization tool for different coatings.
What's the effect on the substrate?
So all of the examples I showed you here were hard coatings on softer substrates. So you do get that kind of, when you get a yield in the substrate, you'll get a cracking in the sample surface. If you have a soft sample on a harder substrate, you can get dramatically different effects. So, for example, we worked on a copper film on a silicon substrate, where you do get some, at very low force, you can get some initial resistance from the copper. And then a slightly different type of failure. It's difficult to explain by hand, but I can show you some data if you have all the time.
Well, about the structure of the sample for that, one thing is if you have a sample that is voltage homogeneous, it's basically a completely homogeneous there, it's easy to see the correlation between the fracture.
personally haven't worked on anything like that.
Can they be quantified in terms of fracture, softness, value?
So it's, what's done in some cases is you measure, you get cracking from the points of the dentist, and then measure the length of backs and stuff like that to a fraction of the street of the experiment. What these are, I mean, obviously the results in these experiments relate directly to fracture toughness. Obviously, tougher materials will be more resistant to this kind of testing. So yeah, there is a good correlation between fracture toughness and impact resistance to this technique.
How do you like content quantification?
So as I said, yeah. So if you measure the crack length